Hello and welcome to another session on seismic analysis with IS1893. I am Surajit Ghosh and in this session I'll cover the basics of static seismic analysis and different factors required to calculate the base shear and design lateral force following the guidelines of Indian Code. This basic knowledge of codal provision is required to evaluate and apply the seismic parameters correctly in any STAAD model, whether it is a building or industrial structure. Most part of India is prone to medium or severe earthquake, and except few small isolated structure like a bus stop or solar panel mounting structure, all other structures must comply with the seismic design requirement. Immediate effect of an earthquake includes severe damage to the structure, including partial or complete collapse. Also, it can hamper in different indirect ways, like surface rupture, landslide, or fire and chemical hazard in the industrial area, which might be catastrophic. That's why all the recent versions of seismic design and detailing codes, including IS1893, 13920, and IS800, are very strict with the design requirements. There are different methods available for seismic analysis, including static seismic, response spectra, and time history method. If a structure is regular with height less than 15 meter in seismic zone 2 and natural period is less than 0.4 second as defined under clause 7.6 and 6.4.3, then only we can use equivalent static method, which is the easiest one and a bit approximate. Else, we need to go for dynamic analysis. Then also, static seismic results play a vital role to scale up the response quantities as discussed in the last part. For proper static seismic analysis, we need to consider several factors, from site-specific condition to building-related inputs. Before we explore those, let's talk about some basics. Earthquake load is not similar to any other lateral or gravity load. If we consider dead, live, or wind load, all these load directly act on the structure. For example, load from a wall or floor finish is applied on the beam or slab. Wind is applied as a pressure load on the exposed surface. If we consider a seismic load, it does not act on the structure. Due to seismic activity, there are some disturbance in the ground in the form of waves, and due to this ground shaking, static condition of the structure is changed. As base of the structure is connected to the ground, it starts to move in the direction of earthquake. Obviously, this depends on the soil structure interaction, but rest of the structure remains static. If we consider the displaced shape of the structure subjected to an earthquake, it seems like a variable horizontal force is applied on it in the opposite direction. So, earthquake load is basically an inertia force which is generated due to ground movement but not directly applied on the structure. It is like a moving bus condition. If the bus suddenly starts to move from a static condition, all the passengers experience a force in the opposite direction, which is nothing but an inertia force. For seismic analysis and design of earthquake-resistant structure, we need to figure out the intensity of this force applied at different story level. By the way, as majority of the mass is lumped at the floor level, we assume that this inertia force is acting at each story level. From basic physics, we know that the equation of inertia force is F equals to m into a, where m is the mass of the body and a is the acceleration. If we follow the same principle here, we can calculate the total force acting at the base level of the structure due to seismic activity. And this force at base is known as design base shear, which is defined under clause 7.6.1 as AH into W. W is the total seismic weight of the structure and AH is the design horizontal acceleration coefficient. This is similar to the original inertia equation, right? So we need to calculate the total weight of the building and multiply it with some acceleration factor to get the base shear in each direction. Base shear might be different in different direction as AH depends on the building dimension. Under clause 6.3.2, code suggests to consider seismic action in each horizontal direction separately if the lateral load resisting elements are oriented in this axis. Else, for any non-orthogonal frames, we need to combine effects from one direction with 30% effect from other direction. All lateral load resisting element should be designed for this combined force. I will talk about this later. For static seismic analysis, we need to calculate the design lateral force at the base level using total seismic weight of the structure and design horizontal acceleration coefficient. But there is a minimum limit of design lateral force. All lateral load resisting element must have a minimum strength to resist any horizontal force. Under clause 7.2.2, code suggests that the minimum design base shear should not be less than a certain percentage rho, which depends on the seismic zone. If we check table 7, we can notice that for higher zone, minimum design base shear value is also higher, which means lateral frames are designed to resist larger force with enough residual strength. We need to cross-check the calculated VB with this VBmin value before we distribute that force at story level. This force is acting at the base level, but we need the individual member force for design. For that, we can distribute this force along the height of the building and in plan at each floor level using the equation mentioned under clause 7.6.3. This distribution factor depends on that floor weight and height of the floor from base. That's why higher floors are subjected to more seismic load compared to the lower levels. We can see similar type of force distribution when static seismic load is applied on a structure, and for this reason, for any tall structure, seismic force normally governs the member design results at higher floor and gravity load at lower level. There are two variables required to calculate the design base shear. First one is the total seismic weight of the structure. This is calculated using total dead load plus a percentage of the live load. This live load percentage depends on the load intensity and it is provided under table 10. For normal condition, load intensity varies from 1 to 3 kN per meter square. Hence, we need to consider 25% of total live load for seismic weight calculation. Live load on roof is ignored for seismic weight calculation, though any permanent attachment to roof is considered. Apart from this, 20% of snow and sand load can be considered for weight calculation, depending on specific condition. How this seismic weight is calculated and assigned in any model for static and dynamic analysis with the help of new mass model generator, that I have already covered in my previous video. You can check that for more details. There is another factor required for base shear calculation, the design horizontal acceleration coefficient, and this is the most important part as it depends on several site-specific conditions and building-related parameters. I'll cover this in the next video. Keep watching.